This video reviews cylindrical coordinates and their relationship to rectangular coordinates, and then we'll talk about how to integrate in cylindrical coordinates and do a simple example. Recall that if I have a point P, X, Y, Z in rectangular coordinates, I can convert to cylindrical coordinates by essentially projecting that point down onto the XY plane here and finding the polar coordinates r and theta that go with it, and then just adding with that information the Z coordinate as well. So my relationships are just those that we have from polar coordinates. X is r cosine, y is r times sine of theta, and the Z coordinate is just the Z coordinate that we use in rectangular coordinates. If you want to go the other way, in other words, if you know X and Y, the rectangular coordinates, and you want to find the polar coordinates or the cylindrical coordinates, use these trigonometric relationships. R squared is X squared plus Y squared, and the tangent of the theta of the angle is y over x. To do a triple integral over a region D in space, first convert your function to a function of r, theta, and z, and because you're now doing things in polar coordinates or cylindrical coordinates, you'll get a factor of r just like you did in 2 dimensions in polar coordinates, and then integrate in some convenient order. I've chosen dz, dr, and d theta. Let's do an example. Let's integrate the function z over the cylinder of radius a, which is some positive constant, and some height h, which is some positive value as well. So we're going to take the cylinder centered there at the origin, parallel to the z-axis, and then its radius is a, its height is h. So we need to do a triple integral over this cylinder. The function is z. I need to convert that function z, and then we're going to have a factor of r because it's in cylindrical coordinates, and I've chosen the order of integration dz, dr, and d theta. To do so, I'm going to project my region down onto the xy plane to determine the polar coordinates first. Because I'm integrating over the disk, I've got 0 to 2 pi, and the radius is a. For a given value of theta, I'll start at r equal to 0 and exit at r equal to a, so my r limits of integration will be 0 to a. And now my z values start at z equal to 0, and then I move up through the region to z equal to a height of whatever the height of the cylinder is, and that's called h. And so we get a triple integral, an iterated integral. All the limits of integration are constants, and that corresponds to the cylindrical region here. And we just carry out the integral now step by step, doing the inner integral first. I'm integrating with respect to z, so I get z squared over 2, and I'll evaluate z from h to 0. That gives me a h squared now. I'll evaluate the next integral, that's integrating r, and that will become r squared over 4. And I evaluate that between a and 0, so I'll get a factor of a squared. Everything's still a constant there. Now I'm integrating with respect to theta, and I evaluate that between 0 and 2 pi, and so I'll get a factor of 2 pi, and simplifying, I'll get pi a squared h squared over 2.